nanoHUB-U, online instruction.
Welcome back to Unit 1 of our course. We are now on the 8th lecture. So in the last 2 lectures, we talked about this how to go beyond 1D and how to take into account a lattice with a basis. Now what we have is an example, a real-world example, graphene, which requires us to think of a 2D lattice with a basis. So what's graphene? Well, that's something I had explained in the introductory lecture, that graphite has these 2-dimensional layers which are weakly coupled, and this coupling is weak enough that people are able to peel off a monolayer of carbon atoms from the surface of graphite, and that's what's called graphene. And what you have here then is this 2-dimensional array of carbon atoms. So here I've shown this red and blue, but they're actually all carbon atoms, and I'll explain in a minute why I've drawn some as red and some as blue. We'll get to that. But what I've shown here is like a unit cell and its surroundings. Of course, the solid itself goes on forever. It's like there's an infinite lattice here. I've just drawn a small section of it for our purpose. Okay. Now, as I had explained in the introductory lecture, for graphene, if you're trying to understand its electrical properties, you can use just one basis function per atom. That's this pz orbitals. And that's a non-obvious statement, but we had discussed it a little bit in the introductory lecture. For the moment, we'll just assume we got one basis function per atom, which means if one atom were a unit cell, then the unit cell would just have one basis function, right? And then the theory would be a little simpler, because then you wouldn't have to consider a lattice with a basis. It would be just a 2D lattice. But the thing is, the unit cell, though, actually needs to contain 2 atoms. And the reason is, you see, the definition of a unit cell is that if you consider a unit cell anywhere, they're all identical. That is, when you stand on one and you look around, you can't tell where you are on that lattice. Now, the point is that this atom is a little different from that atom in terms of its environment. If I stand here, I see 2 people on my left and 1 on my right. If I stand here, I see 1 on my left and 2 on my right. So, in that sense, the environment that this carbon atom sees is different from the environment that this carbon atom sees. And so you can't call one of these atoms a unit cell, because the next one then would be different. But unit cells, no matter where they are, it should all look the same. So what you need to do is take 2 of them and lump it in one and think of that as a unit cell. Then you see it's all identical. That is, if I stand here in this unit cell, I see 2 on my left, 2 on my right. And you go anywhere on this lattice, any other unit cell, and you look around, you'll see exactly the same environment. And so what we do is, when you want to calculate the band structure, as you know, we have to evaluate that quantity. So you stand at some unit cell n and do this summation over the all other unit cells m. So what we do is, we stand here, call that n, and do our summation around there. And because it's periodic, what it means is, I could have stood anywhere on graphene, on any unit cell, and performed that summation and got the same answer. So we stand here then, and we need to do this sum. How many terms in this sum? Well, there'll be 5 terms, because you could put m equal to n, or you could put m over here, over there, over here, over here. So there are 4 unit cells next to it. So those 4 and m equals n. So there will be 5 terms. So what we need to do is write out those 5 terms and add them up. So the first one is m equal to n. That's basically just the matrix describing this unit cell isolated from everything else. And there your diagonal elements, we'll call it epsilon, and the t is the element between a red and a blue on that inside a unit cell. So it would look like a matrix like this, and since n is equal to m, just like before, there's no phase factor involved. This is just e to the power I0. Well, now let's put the m on this one. So you're now talking of that one. Now what you get is, again, a matrix that describes the coupling of this two-component thing to that two-component thing. What does the coupling matrix look like? Well, here you have a red and a blue. Here you have a red and a blue. And the coupling then is between the blue of this and the red of that. So that's why you have a T there, and the rest are all 0. What about the phase factor? Well, remember that Rm minus Rn basically means a vector running from this unit cell to a corresponding point on that unit cell. So you could draw a vector between this red and the red, or you could draw a vector between blue and blue, or from the midpoint to the midpoint. So any one of them, they're all the same vector. So how much is this vector? Well, it has a little bit of an x component and a little bit of a y component. The x component is like that much, which is half of what I've denoted here as 2a. So 2a is that distance. What we want is that much, like half of it. So that's a. So it is a in the x direction, and in the y direction, it's actually that much, which is half of what I've labeled as 2b. So that's b in the y direction. So it's e to the power I k dot, that vector, that's this vector. It is written as ax plus by. Next, we can put the m here. So exactly the same coupling matrix, same story, blue of this coupled to a red of that, same story. But now the phase factor is a little bit different. Why? Because now the vector we are looking at is this one. You see, previously we had this one, now we have this one. Same x component, but the y component is now negative. So it's ax minus by. Well, move on to this side. Here, again, now you'll see the matrix has actually reversed, because it's now the red of that one coupled to the blue of this one. So if you think through it, the t is now in the upper right hand corner, and the phase factor, again, now we want this vector, and its x component as well as its y component are now negative. And finally, for this one, it's the same matrix, because it's red of this coupled to the blue of that, same story, but now the phase factor again a little different. The x is negative, but the y is positive. So these are the 5 things, the 5 2x2 matrices that we need to add up to get the h of k that will be, whose eigenvalues we are supposed to find. So to add these up, these are the 5 terms. If you add it up, you can see as far as the diagonal element is concerned, it's clearly just epsilon. Why? Because none of these 4 have any non-zero elements on the diagonal. The diagonal elements are just 0. So when you add it up, the diagonal is still epsilon, nothing's changed. If you look at the lower left corner, that's where the contributions come from, these 2. That's where you have something on the lower left. If you look here, they contribute to the upper right corner. And if you look at it carefully, you'll see this is the complex conjugate of that, which it must be. Usually, this matrix has to be Hermitian, and so whatever is here, whatever number appears here is the conjugate of that one. Okay. So let's try to write H0. Basically, it is T, we are looking at the lower left, so it's this T plus that T times this quantity, which is k dot x is k, x component of k, so that's kxa, k dot y, that's y component of k, so kyb. Here also it's kxa, but now it's minus kyb, and all of them have a t in front. So this is t, that's t, that's t. So we put it all together like so. And here you'll notice both of these have e to the power ikxa, so I could pull that out. And exponential ikyb plus exponential minus ikyb, when you add that, you get twice cosine kyb. So with just a little trig, you can get from here to that. So this is the expression then for this lower left. And if you work out the upper right, it will just be the complex conjugate of that. What that means is, instead of plus ikxa, you'll get a minus ikxa. You'll notice on both of these, the x component has that minus sign to it. Okay. So now we are ready to move on to looking at its eigenvalues and thinking about that. So we have this H, which is a 2 by 2 matrix, got the epsilons on the diagonal, H0, and as I had mentioned before in the last lecture, when you have a 2 by 2 matrix and the diagonal elements are equal, the eigenvalues are just given by the diagonal plus minus the magnitude of H0. And what is the magnitude of H0? Well, that's this quantity. So if you want its magnitude, you'd have to multiply it by its complex conjugate and take the square root. Now, so these eigenvalues then will all look symmetric around the epsilon. So if the epsilon is here, there'll be for some k, so H0 depends on k. So for some k, you might get a level here. But if you get a level there, there'll be another one down here. So it will always be like a mirror. Whatever you get up here, the mirror image will be down here. Okay? They'll all occur in pairs. Now, where is the Fermi energy? Well, as I had mentioned before, in graphene, I guess this was in the introductory lecture, the number of electrons is such that it fills up exactly half the levels. So what that means is, to accommodate all the electrons, they can all go into this half. You don't need to use the upper half, which means the Fermi energy or the electrochemical potential at equilibrium would be right around here at epsilon. Now, for current flow purposes, as I had mentioned before, what matters is the energy levels right around the Fermi energy. So what that means is, what is really most important is the levels around here. And although I've shown a little gap here, actually in graphene there is no gap, in the sense these kind of touch each other right there. And what we're really interested in is the energy levels right around that region. What that means is, we are interested in those values of k for which the magnitude of H0 happens to be 0. Now, where is that? Now, you might think, well, possibly around the origin, where kx is 0 and ky is also 0. But not really. If you put it in, you can see there. If kx is 0, exponential 0, that's 1. Ky is 0, well, cosine 0, that's also 1. So you get 1 plus 2, so H0 is 3 times t. And that's about as big as H0 gets. So what that means is, at k equals 0, actually H0 is huge. You're getting the levels up here, down here. So those are not the important points as far as current flow is concerned. As far as current flow is concerned, what really matters is those points where H0 is close to 0, small. So how do you locate H0? The zeros of H0? Well, you could do it numerically, which is what we have done here, is this is the kx, ky plane. And what we have done here is what you might call a grayscale plot. That is, we have plotted the magnitude of H0 at different points in k. So you choose a particular kx, particular value of ky, look at the magnitude of H0 and ask the computer to plot it in this grayscale plot, which means if it is small, you make it black, dark. If it is big, then you make it white. So you can see it's whitest right there, because just as we discussed, when kx is 0 and ky is 0, H0 is kind of at its peak. It's 3t. So that part's real white. So where are we looking? We want the black parts. So there are these spots, where it actually goes to 0. So what are these locations in k where actually H0 is 0? Well, you can easily check this. So that point, of course, is kx equal to 0, but ky is not 0, but it's 2 pi over 3. Because if kx is 0, you see, that's out. But cosine of 2 pi over 3, that's minus a half. It's cosine 120 degrees, that's minus a half. And so 2 times minus a half is minus 1, that cancels the 1. So that's where the H0 is 0. And the same works for, of course, minus 2 pi over 3. So those are 2 points there. Another place where this goes to 0 is this one, which is where kx is pi. So because kx is pi, this is e to the power I pi, which is like a minus 1. So it is 1 plus 2 times minus 1. And then pi over 3, the cosine of pi over 3 is half. Cosine 60 degrees, that's half. So it's 1 plus 2 minus 1 and half. That again cancels out. That's how you get a 0. And you'd get a 0 if it was pi and minus pi over 3, or if it was minus pi and pi over 3, and so you have these 4 points. So those are the zeros. Those are the values of k where h0 goes to 0, which means around there, if you looked at the energy eigenvalues, they would contribute right around here, and they are the important ones as far as current flow goes. So what people often do is, rather than use this general expression that works for all k, what you do is you go to one of these zeros and do a little, what you might call a Taylor expansion of that function around that point. So you try to write a simple function, some polynomial, like a linear function of k's, but which works right around there. So let's see how that is done. So supposing you want to find an approximation to this, an approximate function that will work, that will represent this, but right around there. Because exactly at that point, it's 0. But question is, as you move away from that point, how does it change? Well, the general principle is, when you want to do this Taylor series expansion is, you look at the derivative of h0 with respect to kx at that point, multiply by kx minus 0. That means kx minus the value where you are expanding. Similarly, for ky, you look at the derivative with respect to ky, and again evaluate it at that point and multiply it by ky minus 2 pi over 3. And of course, if kx is 0 and ky is 2 pi over 3, you get 0. But as it moves away from that point, this is a linear function that will describe what you want fairly well. So next step then is to evaluate those derivatives. So take the first one. I have to take the partial with respect to kx. So there's a t in front, that's fine. Look inside. Derivative of 1, that's 0. Now when I take the derivative of this, again it's partial with respect to kx. So ky for this discussion is like a constant. So when you have an exponential and you take the derivative, it's like multiplying by ia. So that's what you have here, 2ia. So ia is because I took the derivative with respect to kx. And then we have the old function. Okay, now you evaluate it at that point. So put in kx equals 0, which means this drops out. Put in kyb equals 2 pi over 3. So you get a minus a half. So what you then get is minus iat times kx. So that's this one. Next we need to do the second one. Again, similar story, but now we need to take the derivative with respect to ky. So kx part stays the same, but cosine kyb, when you take the derivative, you get minus sine kyb and then multiplied by b. So that's the b, and then you have the minus sine kyb. Again, needs to be evaluated at that point. So when you evaluate it, you get this minus b square root of 3. The square root of 3 is because you're taking the sine of 2 pi over 3, sine 120 degrees, which is like square root of 3 over 2. So when you put that in, then you get this quantity, and I've written this as beta y rather than ky because it's actually ky minus 2 pi over 3. So what you want to know is how, not the absolute value of ky, but how much it has deviated from that 0. So that's what I'm calling beta y. So overall then, that function can be approximated with this, what you might call a linear function. It's linear in kx and ky. Now, it looks like there's a different coefficient for kx than for ky, but actually those happen to be equal. That's because if you look back at the definition of a and b, this is what we called a, and this is what we call b. And since this angle is 30 degrees, what you can show is that square root of 3 times b is actually the same as a. So overall then, you could write it as minus iat times kx plus I beta y. And this is the result that you often use. So this is the expression for H0 around that location in K space where the H0 is 0. Now you could do a similar expansion around each one of those, but they would all look about the same wherever you go. The details would be a little different, but at the end of it, you'd get an expansion like this. So you might say, well, there are these different pockets of electrons that conduct, and any one of them could be described with that expression. So what would the energy eigenvalues look like? Well, if you use this approximation, then you see the magnitude of H0 is very simple. It's just square root of kx square plus beta y square. So it's like epsilon plus minus at times this. So square, and this is like the magnitude of the k vector, which means out here, as you move away, the further you go, the energy changes linearly. So this is kind of different because we are used to this parabolic dispersion, that is E changes as k squared. Usually you have this h bar square k square over 2m. But graphene is famous for its linear dispersion, where E is actually proportional to the magnitude of k. And because of that, the velocity of electrons in graphene is actually a constant. You see, usually we think the velocity will depend on k. In the sense you think of mv as being h bar k. And so bigger the k, more the velocity. But in this case, because energy is linear with k, you see the correct definition for v, and this is something we talked about in part A of this course, that the correct definition of v is derivative of E with respect to the momentum, that is h bar k. And because E is proportional to k, what you get is just at. dE dk is just at. And so you get at over h bar. And it's independent of k. So you could have electrons in there with different values of k, and the energy will be changing linearly. But the most important point is that although the energy is changing linearly, but the velocity is the same at each k. It's the fixed number for graphene. And how much is that number? Well, you could estimate it. You could put in the values that A is, of course, that length, very well-known number in the sense this is the carbon-carbon bond length in graphene, which is well-known. I think it's about 1.4 angstroms, which is like 0.14 nanometers. And this is like 1.5 times that. So that comes to about 0.2 nanometers. And then there is this one parameter T, which of course, if you're doing first principles theory, you would have been calculating by doing various integrals. But for our purpose, it's a fitting parameter, right? It's something we adjust according to experiment. And in general, for graphene, people believe it's about 3 electron volts, somewhere 2.5 to 3 electron volts. So if you put in those numbers, you'll get a velocity of about 10 to the 6th meters per second, probably a little less than that. But the point here is that it kind of illustrates this whole semi-empirical approach very nicely. That in the semi-empirical approach, we treat that T as a fitting parameter. What do we fit it to? Well, some well-known experimentally measured quantities, like say velocity. If you know that it's about, say, 8 times 10 to the 5 meters per second, well, use an appropriate T so that at least comes out right. And then you can see whether you can use this simple model to understand other things. So as long as you have used one experiment to fit your numbers, and then you are able to explain 10 experiments, then you are obviously doing something right. Okay? Now, so that's the nice thing about graphene, that it illustrates this whole thing in a very almost textbook way. You can easily go through it in a simple lecture like this and see all the steps nicely. Now, there's one detail about graphene, though, we still haven't talked about, and that's what the next lecture will be about. And that is, I mentioned these valleys, and I said that the actual electrons that conduct in graphene, you could view it as if they are in these pockets. And you might say that, well, we got 6 little pockets like this. So it is almost like 6 things in parallel. And this is something then that would have a very direct experimental evidence for that. That is, if you measured the ballistic conductance, as you know, normally the ballistic conductance is 12.5 kilo ohms. It's like about 25 kilo ohms per level, and 12.5 because usually there's these two spins. Right? This is what we talked about again in part A of the course. Now, if you have 6 pockets like this, then you'd think the resistance would be 1/6 of that. Right? So instead of 12 kilo ohms, it would be like 2 kilo ohm divided by 6. But not really, because actually, although this looks like 6, in graphene, there are actually only 2 of these pockets. You call them valleys. So in graphene, there are actually 2 valleys. These 6, it's not the right number. It's actually effectively only 2. And so the ballistic conductance in graphene and in carbon nanotubes is actually 12 divided by 2, which is about 6 kilo ohms. And that's experimentally directly measured. So what we'll address in the next lecture then is, how many valleys are there? Why is it that apparently it looks like 6, but it's effectively only 2? And that's because, of course, we have to consider this Brillouin zone. As I had mentioned earlier, you only look at the states within within the first Brillouin zone. And what you'll find is when you do that, these 6 kind of effectively become 2. That's what we'll talk about in the next lecture. Thank you.